categorical variables that have a lot of their levels. So, for instance, in the rating example where we have 5 different levels, going from not at all likely to most likely, then the approach would be exactly the same. We would select one level to be the base level, and generally we would want to select that level so that it is easier in the interpretation, in the sense that we compare always against that level, and then we create one dummy variable for each of the levels that are not the base. So in this case, we would create a dummy variable for not likely. Let's say we call it dummy 1. It will be 1 if not likely, 0 if else. We will create another dummy variable, let's say dummy 2 for least likely. It's going to be equal to 1 if least likely, 0 if else. We create another dummy variable for somewhat likely, and it's going to have the same approach. And finally, for most likely. So the 4 variables created are, again, binary variables, dummy variables, because they're either 0 or 1 only. And then that would be the approach for a variable, the categorical variable with 5 levels. But this generalizes to many levels. It's just going to be the number of levels minus 1 dummy variables that are created. This is not the only encoding. So dummy variable encoding is the most common to be used in regression. We'll see why that a little later. But there are other types of encodings that we can use. A very common encoding in machine learning is one-hot encoding. So one-hot encoding also uses dummy variables, but it creates one dummy variable for each level. It doesn't leave out a base. So for instance, if we have the variable color, which has three levels, red, yellow, and green, then the approach with one-hot encoding is that we create one dummy variable for each of the levels. So in this example of 5 observations, we would have, if it is red, we have 1, 1, 0, 0. So it would be for the first 4 observations. That would be the encoding that we would have. In this case, it would be 0 here. For yellow, it would be, 0, 0, 1, 0, and 1. And then for green, it would be 0, 0, 0, 1, and then 0. So this one-hot encoding is common for gradient-based methods because some of the methods don't require first to have a y-intercept present, and it makes interpretation a lot simpler by not having to compact or attach the meaning of one of the levels to, let's say, a y-intercept or a particular variable. So one-hot encoding is very common. It is not common at all in linear regression, and we'll see why. But there's another encoding called label encoding. A label encoding is just assigning a numerical value to the different labels. So for instance, if we have safety level, and that safety level is known, low, medium, high, and very high, we can actually label encode it as 0, 1, 2, 3, and 4. So if we have another variable, let's say breakfast, and that variable takes the values never, every day, rarely, most days, with 4 different levels, we can encode it as 0, 1, 2, 3. It doesn't have to be 0, 1, 2, 3, 4, and 5. It can be actually any numerical value. This type of encoding is generally discouraged unless there is some natural ordering of the labels. And but it is actually used in practice. The reason for that is because numerical variables actually do not contribute a lot to the model degrees of freedom. And again, we talked a little bit about that before, but Model degrees of freedom is sort of a proxy um, for model complexity. So actually, a numerical variable brings in less complexity than a categorical variable. So sometimes, if there is some sort of natural ordering on the labels, we can actually use this label encoding. Okay, so let's take a look at the model matrix under different encodings. This example is on the cargo dataset, and we'll see that in a bit. But we want in this dataset to predict the cost of a shipment, and based on the cargo type. There are three types. One is fragile. The other one is semi-fragile, and the third option is durable. So having labels, three levels, we can actually then, if we're going to dummy encode these, have to select the base. So dummy encoding, and again, selecting the base is actually arbitrary. So let's, for a second, suppose that we select durable as the base level. If that's the case, then we have to create dummy variables for fragile and for semi-fragile. So the model matrix, the way that it would look like, remember the model matrix X is an n by k plus 1 matrix, with the first column being a column of ones. So the way that it would work is that we would have dummy variables for fragile. So this would mean that the first observation is a fragile package. The second observation is also a fragile package up to the fifth. Then every single observation is not a fragile package after that. Observations numbers from 6 to 10 are semi-fragile packages, so that's the reason why it has the dummy variable be equal to 1 in that case. And then the rest of the observations from 11 to 15 are actually durable. So that's the reason why both dummy variables are actually equal to 0. Now, the way that we can basically see what dummy variable encoding does is that the meaning of the variable, the meaning of the base class is actually compact. So it's actually translated into the y-intercept, because these two other variables are equal to 0. So actually, that's where everything is. That's why everything is compared against the base class, and then the meaning is actually placed into the y-intercept. So that's dummy variable encoding. This encoding actually makes sense for multiple linear regression, because the matrix X is actually a matrix that doesn't contain any singularities. And remember, singularities when one of the columns is actually a multiple or a linear combination of other columns or another column. So what happens with one-hot encoding? One-hot encoding, you would actually create one dummy variable for each of the classes. And then we would have the first 5 packages are actually fragile, the next 5 are actually semi-fragile, and the next 5 are actually durable. I want you to think about this for a second, and then think about the y-intercept. When we place a y-intercept equal to the values of 1 as a first column, if you want to pause this video for a second and think about singularities in the design or the model matrix in this case, and just think about whether there is a linear combination here, that actually one of the columns of this model matrix is actually a linear combination or a multiple of another columns. So if you want to go ahead and pause the video and then think about it for a second, and then come back to it. Now, I'm assuming that you paused the video for a second, and But in this case, there is a linear combination. Actually, these three columns sum up to 1. I mean, these three columns, if we sum those by row, they will sum all up to always be equal to 1. So the y-intercept is actually linear combination. I mean, the y-intercept column can be constructed as the sum of these three columns right here. So if we do one-hot encoding in multiple linear regression, the X matrix will have a singularity. Okay? So when we do X transpose X, remember that when that is the case, X transpose X, when we are going to take the determinant of X transpose X, that's going to be equal to 0. In other words, we can't take the inverse. When we take the inverse, we're going to get an error. It's gonna the error is gonna be, well, this matrix has some singularities on it, and we saw before what happens in using the LM function in R. You get an answer, but you're gonna get an NA value for one of the columns. So it might be that you get a regression and you're gonna get an NA for the parameter estimate for durable. It's gonna say, well, there's singularities in this matrix, so one of the columns is actually a multiple of the others, and it happens because this is when we do one-hot encoding, it actually creates a problem that one of the columns is a linear combination of others. This problem happens more often than you think. In R actually encodes the variable using the LM function by itself, and we'll see that in the next video. But so we actually don't have to worry about variables encoding the variables by ourselves. But if we use other software like SAS and Python and some libraries, and those, you actually have to encode the variables yourself. So you have to think about whether it makes sense, the type of what kind of encoding first you want to have, and second, whether it creates any singularities on the matrix and on the model matrix. So one-hot encoding, we're not going to use that as for multiple linear regression, but you need to be aware of this encoding, because if you use other libraries other than the LM function in R, or if you use other software like Python, you might have to do the encoding yourself. So you have to, or select an encoding based on the different encodings that the particular package has. So it's you have to be aware of these different kinds of encodings. The label encoding, it would just be, in this case, assigning maybe 1 to the fragile packages, 2 to the semi-fragile, 3 to the durable. In this case, it doesn't make sense as much to use label encoding, because there's not like a natural ordering on the labels, on the levels of this particular variable. Granted that you could say, well, maybe fragile, we should assign it a value maybe lower or higher than durable, so it might have some sense in this case, but we generally discourage using label encoding unless it is something that makes specific sense. Because remember that when we do interpretations on the parameter estimates, we will be interpreting it as the slope as a change in x. So a 1 unit change in x, what happens on average to the variable y, to the response. So if it doesn't make sense to change, so a 1 unit change from let's say fragile to semi-fragile might not make sense numerically. And again, we'll see more about that as we go along. So we'll go and do an example in R so that we can practice a little better on this. But these are the 3 main encodings that you need to be aware of. We will be exclusively using dummy variable encoding, but it is important that you recognize these other types. We will not be using at all one-hot encoding, but for projects, I will let you decide on if you think there is some sort of advantage of using label encoding in some cases, specifically if the variable has some natural ordering on it. So let's so we'll switch to some code now, so that we can practice these types of well, at least dummy variable encoding, and how the variables, the levels of the variables can be visualized in R.